the US to Israel, and she's done lots of wonderful work, and Shafi was her PhD advisor. So she was also a student and a speaker at Women in Theory in the past. So let's welcome Elette.
Hi, everyone. Good morning. Hopefully I'll keep the energy reasonably high in case people are a bit tired. So indeed, I'm a cryptographer. Right now, I'm faculty associate professor at Reichman University in Israel, and also a senior scientist at NTT Research. I had to think a little bit about what to talk to you guys about. I kind of toyed around with a couple options. I've decided this is what you're going to hear. So this will make sense as the talk goes on, but I'll be talking about something called zero knowledge on distributed data, and talking in particular about how this gives us useful applications within some setting of cryptography. So this is cryptography in itself, of course. I'm going to keep things relatively high level. At some point, I'll dig a little bit deeper. But kind of collectively, this is based on a line of work, two kind of combined lines, one together with Dan Bonnet, Henry Corrigan-Gibbs, Niv Gilboa, and Yuval Eshai, and the other one with the authors over here. So Niv, Yuval, and Ariel. And at any point, feel free to jump in if you have questions, if you have comments, if you have complaints. We'll see how it goes. Okay, so push everything to the side for a second. And I want to talk a little bit at a high level about what is my research kind of geared at. And the core focus of this, I would say, is centered around this notion of secure multi-party computation. Okay, so what is this thing? Well, the goal is that we want to jointly compute across sensitive data without revealing the data itself. Okay, so more concretely, say we have a collection of parties, maybe the people in this room. Each of you has a deep dark secret, XI, okay? Don't tell anybody what your secret is. And the goal is to design protocols for us to communicate back and forth, such that at the end of the day, if we're given some public function F, we want to know what is F on our secrets. Maybe this is some statistical information. Maybe this is who is, makes the most money, or who does something of this form. But ultimately, at the end of this discussion back and forth, we will all learn F applied to everybody's inputs, but in a way that you don't learn anything else about the inputs. Okay, so for example, if we learn who here makes the most money, we've got some candidates. It's maybe not some of the students, maybe it is blockchain, of course, right? So once we learn this outcome, we know something about other people's inputs. For example, I know whoever makes the most money makes more money than I do, and everybody else also makes less money than them. So that's some information, but you can characterize that basically the only information that's being revealed is what can be inferred by your own inputs beforehand, together with the function output. Okay, and I'm a cryptographer, I assume the world is out to get me. So I even want to be able to do this and to have this guarantee, even if a subset of these parties of you folks here are acting adversarially. And I'll talk a little bit later about what exactly do we mean by that. Okay, so the first question you might ask, this sounds great, sounds a little bit too good to be true. Is this even possible, secure computation? The answer is yes. So this is something that goes back to a beautiful line of works from the 1980s. But in one of two cases, either, for example, if I can assume that a majority of you are acting honestly and following the protocol, or if I can assume that at least everyone kind of in the world has some computational bounded power. For example, they can't factor the product of two large prime numbers. Okay, so this is, you can see, we have some culprits here in the audience. This one is Shafi. And so this is kind of where we were back in the 80s. And over the last decades, there's been a tremendous amount of work and progress in this area. And kind of fast forwarding to today, roughly speaking, where we stand is that for specific targeted tasks, this is there already. Okay, Google is using some of these protocols. A number, Signal, for example, Telegram, a lot of different places are using secure computation protocols. But right now, kind of where this is being used is more for like specific functions F that have targeted protocols designed for them. I was running over here a little bit, so I'm a bit winded. Okay, and for general computations, this I view as a very exciting kind of border here, where we're not quite there. And I'll talk, this is kind of the main message of the talk today, is going to be that the costs are still too high. We're trying to get the costs down. That if I don't care about security, I can do it with some cost. In order to achieve security, you have to pay more in communication, computation, what have you. Okay, so this is mostly where I'm going to be focusing at, of looking at general functions F and trying to figure out how can we try to decrease the overheads of these protocols. Okay, and indeed, so when I'm looking at overhead of these things, in particular, I'm interested in the communication overhead. And there's a number of reasons for that. First of all, from a theoretical standpoint, it's a very crisp, nice kind of thing to study. But also at a practical level, turns out computation is becoming cheaper and cheaper and cheaper. And communication in a lot of different settings is the actual concrete bottleneck. Okay, so let's ask ourselves, what is the communication complexity of securely evaluating some function F? Okay, remember, so the baseline here, if I don't care about security, of course, there's an entire area of communication complexity, also a very interesting area of theoretical computer science. I'm kind of not going to go into that, where if there are specific functions F, maybe you can do better than what I have written here. But in any case, no matter what the function F is, I can always just, so let's say I'm just looking at two people here. I can just send you my input. You compute F on X and whatever your input is, Y, and you send it back. Okay, so this is always like, this is sort of our ground comparison point. Okay, so what about secure computation? I told you we can do this since the 80s. And it turns out that from the 80s up until 2009, all of the solutions that we had required communication complexity that instead of scaling just with the input and output, scaled with the representation size of the function. Okay, so slightly more concretely, suppose that you take this function and you express it as some circuit. Okay, so say like a Boolean circuit or arithmetic circuit over some ring, where your gates are additions and multiplication gates. Okay, and unfortunately, in many cases, this function can be much, much bigger than just the inputs and outputs. Okay, small input, small output, huge circuit. So this, by the way, on its own, is like, I could talk a lot about it. This is a fascinating area. It really seemed like we were kind of stuck. Was it even possible? In 2009, you've probably heard of this notion of fully homomorphic encryption. In fact, so this is the Gödel Prize of this year. This was Craig Gentry, Zwiga Borkowski, and Vinod Vaikunthanathan. So this fully homomorphic encryption allowed us a way of getting the communication complexity much lower. And just very, very loosely for those who haven't heard of it, FHE is something that kind of allows you to compute on encrypted data. So roughly speaking, I would send you an encryption of my input. You would sort of do the computation on this encrypted value and send the answer back. And of course, I've stuck in here, there's one other approach that we know how to do this based on something called homomorphic secret sharing, which also I could talk a lot about. Okay, so in theory, this is fantastic. We have very small overhead, we're happy. Fortunately, in practice, there's a lot of gap there, okay? So certainly in certain applications, FHE and so forth are very practical or can be quite practical. But in the general case, these things are very expensive. So for example, even though this is asymptotically fantastic, the constants here are kind of worse than the original version. Okay, so in practice, the sort of the baseline here is going to be taking whatever the circuit representation is, and the communication that we require or that these protocols have will be kind of some number of ring elements, whatever the circuit is over. So it's either 0, 1 or some ring R. For every single multiplication gate in the circuit, we have to each communicate some constant number of ring elements. Okay, this constant I'm going to denote by alpha. And I'm not telling you what it is yet. It depends a lot on different settings. Okay, so actually let me pause here for a second. Are there any questions so far? Okay, so indeed, what is this alpha? And this, of course, depends a lot. And before I get to that, let me say a little bit about the high-level structure of how these protocols are designed. Okay, so essentially every protocol that I know that gives you the security that you ultimately want. Okay, so this is the fiery devilish fellow over here. When I was talking about adversarial behavior, ultimately we want to be able to protect even against people who are doing whatever they can to try to destroy the protocol. Okay, this is the goal: security against that guy. Okay, you don't want to run into him on the street. Actually looks very cute, doesn't he? Okay, but in order to get to this high level security, what happens in these protocols is that you first achieve some weaker notion of security, which I'm going to call passive security. Okay, and here you're sort of assuming that the bad guys in the protocol are actually following the steps that they're supposed to be doing. So if it says, take these values, multiply them, and send that as a message, that's really what he's going to send. Okay. Okay, and interestingly enough, even against this setting, there's a lot to hide and to protect. Because, for example, it could be trying to sort of learn more information, combining different parties together who are not supposed to share information. And this could actually reveal secrets. Okay, so what happens is you first design a protocol against this weaker setting, and then you somehow boost up. This boosting is going to be a big focus of my talk. Okay, so this framework was originally put forth in this GMW. This is Goldreich, Micali, and Wigderson. And I'll say just kind of one sentence about how do you do this. So in the original work here, what they did is that each time you would send a message, you'd basically pair along with it some sort of proof that this was the right thing you were supposed to send. Okay, so that was the original kind of compiler approach. Since then, there's been a lot of different things. Things like maybe you do multiple executions of the protocol and you kind of open up some of them, something called cut and choose. You use kind of authenticated beaver triples. Don't ask me afterward what on earth does that mean. These are certain useful correlations. But the bottom line, this is still a very interesting and important area of research of doing this. And one of the reasons for that is that this arrow tends to incur a lot of cost. Oh. Okay, so going back to this alpha, this kind of constant overhead communication cost. In some of these settings, you can get passive secure protocols with very small alpha. Of course, you could hope for even sublinear here, but suppose even like alpha equals 1, which is doing pretty well. But so prior to kind of this line of work that I'm going to be talking about, the best possible thing up here required at least twice the communication overhead. Okay, this is kind of in the good case where your circuit was over a large field. If you were over a Boolean circuit, sometimes this overhead was as much as like 40. Okay. So, so very kind of the takeaway, maybe piece of this talk, or one takeaway, is that by using the techniques I'm going to be telling you about, we can get this so that the overhead is sublinear in the circuit size. Okay.
So that works where the circuit size several dozen. It's not affecting the communication. You're ignoring that. You just look at the line.
Yes, yes. So you can actually formalize a separation of these two different settings, for example, based on computational assumption. So these things, either in the honest majority case, say black box use of PNG, or even information theoretic, In the dishonest majority case, which I'll just briefly mention, you can also get results in like an offline basic model.
In which case, this is also relevant because you still could talk about the active security, but it's a different story.
For dishonest majority?
Yeah, no, I mean,
Or for the,
even
like,
for honest majority, this alpha, there's a question of going to.
Yes, yes.
But that's not captured by this.
So, okay, so I'm not sure.
But that's what I'm asking is, here you are covering the issue of improving from weak to standard with the line of work where everything's size of circuit.
Yes.
I'm saying there are line of work which sort of separate out the size of circuit and communication. But also there you have to go from weak to act.
Yes, yes, yes.
Is this relevant to all of it?
This is mostly relevant just to the lower end, to the efficiency stuff. But for example, as a feasibility statement, you can get this also if you put heavy assumptions on. For example, if I put snarks or snogs or things like that, that gives you. The problem is that the efficiency is.
Okay, my question is about the.
Okay, ask me after. Yeah. So again, so this is kind of, yes, within the setting, which is, so there's different ways of formally defining a separation here. Certainly also, maybe another thing I should mention. So when I say like in theory versus in practice, like the stuff that's being implemented, aside from a couple of startups, I suppose, is in the in practice category. Okay, so pausing here again, any questions about the high level kind of goal? So again, the goal is to do this transformation where the communication overhead is sublinear in the circuit size.
So are we amortizing overlay the same?
Okay, good. Let me explain. What do I mean by amortized here? Even just one execution, but what I mean is that the final communication, so this is communication like alpha times size of C times number of parties. This will be that plus something sublinear in C. So it's, it's like alpha plus a little bit, but if size of C is large, this is what I'm amortizing over.
Could you explain again what you're assuming in weak passive security? Like what is that adversarial allowed to do in this?
Good. So the adversary is required to follow the protocol. So if we have some specification of, for example, sampling random bits, it has to sample random bits, a true randomness. And if it says, the code says for the next message function, given the values here, compute this and send that to whoever, that is followed. So that is what it does do. And the question is, where is it cheating? Like, why is it adversarial at all? So for example, in the honest case, you're not supposed to share information with anybody else. So I'll give you something and I'll give you something. And I'm assuming that you are not combining these pieces. But in the semi-honest case, there's some fraction of people who are corrupt, and we assume that they could be colluding with each other. So their secret, like whatever I'm sending you to, would come together. Okay, excellent. So, the star of the show, or at least the title of this talk, is this notion of zero knowledge on distributed data. And let me take this step by step. Okay, before anything else, let me mention zero knowledge on its own. Okay, so this is something, again, Shafi did a number of very influential things, including zero knowledge. And in a zero knowledge interactive proof, we have the following setting. Okay, there's a prover and a verifier. There's some public language, think of maybe an NP language, graph colorability, something like this. And both of us know some candidate graph, say, some input X. Okay, and the prover is trying to prove to the verifier, this graph X is 3-colorable. It's in the language. Okay, so as an interactive proof, we want it to be complete. That is a function of talking back and forth. If P is honest and X truly is in the language, then at the end of this communication, the verifier will accept. We want soundness, that if this graph is not 3-colorable, if X is not in the language, then no matter what a cheating prover is doing, then the verifier will reject with some good probability. Okay. or kind of the converse here, sorry, not the converse, the contrapositive. If V accepts, that means X is in the language. And this tricky third property of zero knowledge says that even if the verifier is corrupt, then through this conversation, it still doesn't learn anything beyond the fact that X is in the language. Okay, so for example, suppose here we're talking about some language that's not easy to decide. For example, graph 3 colorability, as far as we know. And this is kind of interesting when the prover has some extra power or knowledge. For example, maybe it has a witness for 3 colorability of this graph, or maybe it has extra computation power, it can solve problems. And what we want to protect is that the verifier doesn't learn anything beyond what it could have known from the beginning. So in particular, for example, the prover cannot just say, hey, look, here's the witness, which of course would convince the verifier, but this is information beyond just the fact that X is in the language. And again, kind of magically, you can do these things. Just maybe a couple comments about graph 3 colorability. So suppose that we have this graph. One way that you can run such a protocol, and I'm not going to get into specifics of how do you implement this. So suppose that I'm the prover, I'm trying to convince you as the verifier. What I can do is I can randomize the colors, choose kind of a random reassignment of the colors of my 3 coloring. Okay, and I cover up all of the nodes. So I color the graph, I cover up the nodes, you come into the room, and your challenge, you say to me, give me this on one particular edge, say a random edge, uncover the 2 nodes of this edge. We open them up, you check, are these one of the 3 colors you're supposed to use? And is it the case that they're different? Okay, if not, then I'm caught and busted. But if so, then with some probability, so you would have to kind of amplify, you do this many, many times. But kind of the important thing is that if this graph is not 3 colorable, then however I choose the coloring, there is some edge that is miscolored. And you have some probability of finding that edge. So if you amplify enough times, you'd eventually get convinced that this has to be 3 colorable. Okay, now, but why is it zero knowledge? Well, what have you learned by this instance? Okay, and when I say amplifying, I mean each time I have to choose a random kind of remapping of what the 3 colors are. So if this was white before, now I'll choose it blue or whatever. Okay, so this is zero knowledge because the only thing that's being revealed to you in this execution is an edge and 2 colors which are different. That's something that you can simulate on your own. You can go to the side and you can do that on your own. Okay, so this is an example of the type of framework of a zero knowledge proof. Okay, so this is this beautiful classic notion from the 80s. And now starting with a bit of a twist. So what we put forth is a modified version of this, where you have zero knowledge interactive proof again on distributed data. And what we mean by that, so whereas before there was one verifier that I was trying to convince who knew what the graph was, who knew what X the statement was. And now we're considering a case where maybe there's multiple verifiers, maybe a few of you are running this, but it might be the case that no single verifier even knows X completely. Okay, so you guys know this part of the graph, you know this part of the graph, or maybe you have some sort of secret sharing of information about the graph. Okay, kind of what we need is that there exists some known linear combination of these pieces that combine to give you X. So for example, pieces directly give you that. Excellent.
So say you have 2 different and let's say it's a patent litigation case, and they want to prove that, let's say that their source code is different or subsumes one another or something, and they don't want to reveal the code to the judge. So neither one wants to reveal. But they both have pieces of this secret, which they can do computation on. They want to prove
I like that. And actually, so I should mention that indeed, if you kind of throw generic secure computation onto this, this is like a special case of secure computation. Okay, but because this is a special instance, you can hope for much better protocols. And in fact, we're sort of going to use this as a tool to build better secure computation. Okay, good. So a little bit more about the setting here. So the verifiers as part of this can communicate back and forth, and in particular can, we don't really need that you share randomness, you can kind of sample randomness and communicate, but there is going to be communication, but we want that communication to be relatively small.
Can they be correct, the verifiers?
Yes, good. So, okay, so let me kind of go through what are the three comparable properties that we want here.
So maybe I'm not understanding the setting, but it seems to me that if you're splitting up the knowledge of X in some way, there are cases where verifying would become impossible. Like what if there's two verifiers and it's a bipartite graph and like, you know, each verifier has a set of vertices with no edges between them. Like, how do we get around situations where verifying seems impossible if you only have—
Okay, good. So if the verifiers are honest, we will still be able to do things like that, which is a little bit tricky. And it will be kind of how what is it that you're communicating back and forth. But you're right that in certain cases, if verifiers, subsets of verifiers can be corrupt, things get a little sticky, and that'll be down at the bottom of this slide. Okay, so first of all, kind of the similar things to begin with. So we do want that if the prover is honest and X truly is in the language, we want it to be accepted. And note, by the way, that the prover does know the statement completely, knows the input. Okay, the zero knowledge property is going to be an analog of before, but I want to emphasize something in particular. Okay, so suppose the prover is honest, but a subset of the verifiers is corrupt. Okay, this is the analog of zero knowledge from the previous slide, where the verifier, there was only one, was potentially corrupt. What we want is the exact analog that by communicating in this whole protocol, this subset of verifiers learns, of course, that X is in the language, and it learns what it knew before, which is these pieces of X, but it doesn't learn anything else. And in particular, that means we don't even want to reveal other pieces of X. Okay, so before, that's not something we had to consider because both sides knew X completely. But now there's additional information that we want to hide. Okay, and so now for soundness, and this indeed gets a little bit more fine-grained. So if, let's suppose, first of all, suppose that the prover is corrupt, but all the verifiers are honest, then it's a bit straightforward. We want it to be that if the verifiers accept, that means X is in the language. Okay, what becomes a little bit more complicated is if some of the verifiers can collude with the prover, if they're all corrupt. And the reason for that is to, what does it even mean? What is it that we're really proving? We're proving that this combined thing is in the language, but note that the verifiers have some power over kind of changing what this combined thing is. Okay, so I'm not actually going to go into detail about it, but it does make sense if it's the case that these pieces of X have some sort of robustness property. So for example, if it's the case that if I just took the set of honest verifiers that already uniquely determined what is X. So then it kind of makes sense. What does it mean that I'm proving this X is in the language or not?
So take it back. My example made mistakes. In your case, the verifiers are distributed, not the prover. What I was thinking was it was the prover that was distributed and the verifier was distributed.
Oh, I see.
Verifier. And the two pieces of software were held by provers. We're trying to prove joint statement, but not reveal to each other.
I see. So, okay, so maybe a different example though. Suppose the prover is like an individual, and part of this is my banking information, and part is my medical information. So I know both of these things. The bank knows one, the hospital knows another. And I want to prove to an insurance company that I have enough money and that my medical situation is good.
Confuse me. Prover knows everything.
Yes.
The this example, and the verifier is an insurance company.
So, yeah, say like one of them is insurance, one of them is, yeah.
And I'm the individual that
Yes.
tries to prove everything is up. Okay. And they don't trust me really, but they're going to use other verifiers.
Yes, yes.
as
So for
well.
example, say the bank trusts the hospital and vice versa. Yeah.
When you say corrupt P plus VIs, they're not all colluding together, right? Because in that case, then P could just give X to VIs. So it's like corrupt P and corrupt VIs is how I should interpret this.
Oh, just a second. So, so in terms of revealing X, if the prover is corrupt, we're not really trying to hide X from anybody.
I see.
Then in any case, that would be more up with zero knowledge. So this is still, I'm still talking about a soundness, and here, yes, I do mean that they could be colluding with each other.
There could be an extra witness actually suggesting we could verify it.
Say that again?
There could be an extra witness.
Yes, yes, this is also true. So kind of as before, also if the prover has an extra witness, as before, you still don't want to reveal the witness. This is something kind of on top of that.
So do we consider a parallel setting where the prover's interaction with each verifier takes place at the same time, or they could be a concurrent where they could take place at different, the protocols between P and VI and probably some other major take place at different.
So the protocols that we design or kind of consider are in some sort of synchronous setting. But for example, you can actually you can even do a very simple communication structure where the prover sends out one thing. The verifiers need to kind of choose a random string together and send each other some answer based on that random string and then decide. So you can get better efficiency if you have multiple rounds of communication, in which case we do consider a synchronous setting, but even the simple version gives you something. So, okay, I'm identifying that I was a little overly excited with the amount of content I wanted to squeeze into this talk, so we'll skip some future stuff. But this is good. I want to at least give you some high-level ideas of things. Okay, so one of the high-level comments here is that in this setting, in this distributed data setting, there's some interesting new questions that sort of open up. So for example, before with standard zero knowledge, if the language L is simple, it's a little bit pointless. Okay, so for example, suppose that verifier one knows all of X and the language is something very simple that, for example, if I look at the different symbols of X, there's some quadratic constraint that's satisfied by them. Okay, I can give you a very simple zero knowledge proof. I don't send you anything. Okay, and you go to the site and you check with X, does this actually satisfy? Okay, so in the standard case, this is only sort of interesting for hard languages L. In our case, that's not the case. In our setting, that's not the case. Okay, so and here this is because nobody can check this directly on their own. For example, maybe that my relation is that if I take this symbol that you're holding times this symbol that you're holding is equal to this symbol that you're holding. This is already something that's very interesting. Okay, and so I'll say a little bit about new applications of this setting, of this tool, which has different kinds of complexity goals compared to things that that people have looked at or like mostly considered in the other case. So in particular, I'm going to be really interested in how much communication is going on here. What is the sort of the proof size that the prover has to send to the verifiers? Okay, so I'm going to give a little bit of an abbreviated version of this, but I want to give you a high-level flavor of sort of where do we build these things? How do we get them? I will not go into depth. And I also want to show you how can you use this in order to get this arrow up, this compiler from passive to active security in secure computation protocols. Okay, the punchlines, especially if I don't get to some parts. So for the first part, I want to kind of emphasize, so we can get very low cost protocols for simple languages. We're simple, for example, degree 2, constant degree, so forth. And the low cost is going to be very small communication, sublinear even in the input size of the size X. Okay, and using this, the punchline of the second part is exactly, we get this arrow that goes up from certain protocols with passive security up to active. This is malicious, is sometimes used instead of active security, where the additive overhead is sublinear in the circuit side. Okay, so the construction part, as I said, I'm going to keep high level, but as a function of this, maybe I'll also teach you guys a little bit about something called PCPs. Okay, so probably a lot of you have seen this, but at a high level, so a PCP, or probabilistically checkable proof, right? This is a setting where a prover takes the X and witness, if they have one, and spits out some proof, potentially long proof, pi, where the verification procedure chooses a small number of positions of the proof to check in order to verify that X is in the language. Again, if I put things in blue or things that the verifier sees, so the verifier knows the statement and kind of looks into a small number of positions of this proof. And this is this fun thing where they said, you know, what if you, in order to review a paper, you demanded that the authors, instead of writing this proof, actually wrote a PCP. Okay, and then as the reviewer, you only have to look at 3 parts of the proof and decide whether it's correct or not. Wouldn't that be fantastic? Okay, and this is so something back in the 90s, it was shown that for any NP language that you can actually achieve such a thing. Okay, so I'm not going to talk about how to achieve any of these things, but I want to give you just a little bit of a flavor of variations of PCPs that exist in the literature. Okay, so perhaps fewer of you have heard of something called a linear PCP. Okay, it's a very similar sort of setting where the verifier sees a statement, the prover generates this proof, and the verifier doesn't get to see the proof in whole. Okay, over here, the verifier got to look at specific symbols of the proof. And here it's actually more power to the verifier, where what the verifier gets to do is say, give me this linear combination of the proof symbols. Okay. So they give us like this is specified by some coefficient vector, and you get the inner product of the coefficient vector with whatever this proof is. Okay, so it's still shrinking. I'm only getting a little bit of information, but it's a little bit more powerful because, for example, I can capture PCP queries by just specific instances where I just have like a 1 in a given position. Okay, that would pull out one symbol of this thing. Again, because of the stronger power of the prover, you can get some better properties. Sorry, the stronger power of the verifier. Yeah, some of you maybe didn't know all these field of flavors existed. But I want to emphasize, so remember that we're in a setting where the verifier does not know the statement. So I want to kind of step over into that regime. And there does exist a notion called Pcp of proximity, which is similar to PCP, except you'll note here that the statement is no longer blue. So in this setting, and protocols for this exist, the verifier only gets to make access into symbols of the proof and also symbols of the statement. So on the plus side, this is saying the verifier even has less. Downside of this, or one of the downsides, is that you can't actually ever guarantee through this process that X that's written here is in the language. Why? Because, for example, maybe it's almost in the language, but one symbol is flipped. There's a low probability you're ever going to hit that symbol. So the only thing that you can actually assert in such a proof system is that whatever X is written here is close to the language. Doesn't have too many symbols away from something that is. Okay, this box is what I've been waiting for. This fully linear PCP. Okay, so kind of take the squeeze of these two things. This is a notion that we put forth in a paper back in 2019.
It's X is close to the language, or is it there's a proof pi prime that's close to pi, which is correct?
It doesn't. it doesn't matter so much, like we don't really care if there exists a close proof. The final conclusion at the end is just that whatever is here is something that is close to the language, but it's kind of just a tool along the way. Okay, so this is a fully linear PCP, as maybe you can extrapolate from the pictures here. It's a setting where the verifier does not know the statement, and the queries that the verifier makes are linear queries. Okay, but instead of just being over the proof, now they can be complete linear combinations across the proof and the statement. And so what are kind of the pros and the cons? Well, so these are stronger types of queries than this, of course. And because of that, because, for example, my query can kind of smear together some linear combination of all the symbols of X, you can actually assert in some of these protocols that if the verifier accepts, then X itself is in the language. Not just that it's close, but it is in the language. Okay. Fully that it's fully linear, like linear in X and also linear in pi. Yeah, I'm not sure it's the best name, but
Before it was just in.
yes, yes. Okay,
So
so
in other words, you don't read all of X, or you do.
you need to sort of so in the kind of the model here, the query answers are generated as a function of all of X. But the verifier does not get access to X, it only gets linear query access. So again, it's a lot like here, this is compressing in the sense that, you know, here you get like 5 symbols, here you also get 5 symbols, but they're computed as a function of all of the symbols, yeah.
Proofs are not like that. Presented in some error correcting form, and also you're not.
In some sense, it implicitly is then. If X is already written in error correcting form, then some of the symbols that are written down are already linear combinations of all of X. That is yeah. Okay. Good. And so in fact, for actually each of these things, you can also consider a zero knowledge version of the thing, where the extra zero knowledge is that as a function of, for example, the verifier queries, you don't learn anything beyond that X is in the language. So in particular here, for example, you can design the protocol so that the queries are not actually leaking information about X directly. Okay, so maybe I'll take the quick vote. Do you want to, I can either talk about how if you have such a thing that gives you zero knowledge on distributed data, or talk about how you can use zero knowledge on distributed data to give you the arrow. Which one? The first one. Okay, I think I will do that. Otherwise, there's a lot for the other stuff. Good. So suppose that I have such a thing. Okay, and actually let me maybe briefly. Okay, so let me pause and say, are there any questions about what this object is? So slightly more formally, there's some sort of prover algorithm. The prover has the statement and the witness and generates this proof. And the verifier gets to make queries that are describable as linear combinations, so it's some coefficient vector here, and gets as answers the inner product between the coefficient vectors and the concatenation of these two things.
Wait, how is this hiding X at all? Why can't you just like do indicator functions to get X out? I don't totally see that yet.
Okay, good. So you're right, it's sort of like it can be made zero knowledge. I'm not really saying much about that,
Okay.
but you can make it that sort of think about it as like honest verifier zero knowledge. That if you do the queries you're supposed to, then you won't.
You're not supposed to hide it, are you?
In this case, so I haven't written here, we will be interested in hiding X. And kind of just why is it okay to think about honest verifier zero knowledge in our setting? The answer is going to be because, so we have these multiple verifiers and sort of they'll jointly generate the queries. So this will enforce that the queries will actually be honest. Any questions about? Okay, excellent. So suppose that we have this. And again, this is kind of like an abstract thing on its own with some, magical query answering that's not clear, like who's doing this query answering, but it somehow comes to the verifier. And now let me describe to you an example of how you can use NUT to give this zero knowledge on distributed data. Okay, so the prover starts with X, maybe some witness, and first runs this proof protocol to generate the proof pi. Note that the prover, it's not necessarily okay to just send the proof. Okay, and why is that? So kind of going back to here, remember that this zero knowledge property is only guaranteed given these query answers. In particular, the zero knowledge property doesn't expect that the verifier can see the proof. But don't worry, that's not going to be a problem. You can just, the prover will take the proof and additively secret share across the two parties. So what does this mean? This means this is actually just a totally random string, and each symbol here is such that this symbol, because this symbol is the real symbol of pi. Okay, so now we have kind of this piece over here. Now the verifiers will jointly decide the query. The verifier queries from the fully linear PCP. Okay, how do you do that? Well, there's different ways of exist, like coin tossing protocols where the two of us can just generate a random string together that will be honestly random. Okay, that defines this sort of compressing linear function here. Now, each verifier, neither verifier actually has pi together with X, but we have something. Let's suppose that if I take this part, suppose that, for example, this verifier only has these symbols of X and this additive secret share of pi. Okay, well, say that it just computes this linear combination of whatever it's got here. This verifier does the same. Now, what are these two answers? How can I combine these to get the actual answer of the verifier query? In this case, I could just add them together. Why is that? So think about this as describing some linear combination of, for example, now I've got zeros here and actual symbols in some secret sharing. And the linearity of these queries, the fact that this is a linear function, means that you can kind of do this in a different order. Either first add these together, then take the linear function, or take the linear functions and then add it together. And I claim that this, so now the verifiers, each of them, they exchange these values, they indeed add them together. As in a function of that, they can decide whether to accept or reject. And I've described it as sort of a one-shot process. It's not really a problem if you have interaction and you need to do multiple rounds or things. The exact same structure works. Okay, so this gives, we want completeness. By the correctness of this thing, this will give us exactly the complete, like follows from the completeness of the previous slide. Soundness. Actually, let me get to soundness in a second. Why is this zero knowledge? Okay, this is coming from the fact that this tool is going to be zero knowledge. And the only thing that you're really revealing here, you're exchanging just the query answers. Okay, so the only thing that the verifiers are learning are exactly the answers to these queries. And why is it sound? Okay, well, so let me kind of do the simple version. Suppose that the verifiers are both honest. Okay, then soundness here is going to exactly follow from the soundness of the fully linear PCP system. Okay, good. So so let me just kind of mention what do we know, what do we actually know about building this fully linear PCP? Well, it turns out that many PCP or regular linear PCP constructions from the literature actually already have this natural structure. For our particular setting, where we're interested in really pushing down the proof size, like what is the length of pi? Okay, I kind of purposely wrote pi is something short here because this is what we want and we can achieve for simple languages. So here, for example, the pi is even sublinear in the size of the combined x. Okay, and for this setting, so indeed, if I'm looking at these simple languages here, so these are like x's, which are vectors of field elements that are where the language itself is expressible, say by degree 2 or some constant degree expression. Then we can get roughly, say, like square root of the size of the x for a one-shot thing. What is an IOP? Well, I didn't really tell you this. This is called an interactive oracle proof. This is like a kind of an interactive version of a PCP where you have to do rounds of communication back and forth. And here we can get the total combined proof size to logarithmic. You'll note I didn't write any computational assumptions here. There's a very good reason for that, because we don't need any. This is a purely information theoretic object. And here, so the error, the soundness error in these cases is like 1 over field size. So if your field happens to be very large, this is already fantastic. But if you have something small, say I'm looking at Boolean, my statements and my things are just bits, this is pretty crappy. But don't worry, because you can do a natural amplification by, I won't really explain how, but you can do like basically embedding your elements into a larger ring or field extension. You can ask me about that afterward if you're interested. Okay, so I
1 second. The picture.
Yeah. Oh, sorry. Which picture?
One back. It's not the proof.
This is a secret share of the proof.
And the verifier somehow have a signature.
The prover sends it. The prover sends the secret shares. This is part of the
sorry. I wasn't listening for a minute. So he sends the shares and using. So these pies that they have are different. It's like pi 1.
Correct.
Pi
Yeah. You're right. These are.
Okay.
Yeah.
So they have shares. And together and they can talk to each other.
Yes.
So, but they might need the prover again. Or do they just need an initial proof?
And so in there exists, it depends on what your original linear, fully linear PCP setting is. In that case, if it's just like you can make one-shot queries, then you just need to do it one shot. If the original thing requires more communication, then you sort of inherit executive structures. In particular, these the IOPs, the interactive oracle proofs, this is the thing where in each round the prover like sends an additional piece of time. Okay, so due to time, let me very just briefly. I'll keep it quite brief, but I do want to just give you a very, very high level view of how do you stick this tool in to give you such a compiler. Okay, so here's the very high level plan. Remember that the goal now is to go from a secure multi-party computation protocol against just passive adversaries and boost up to kind of enforce security even against active malicious adversaries. Okay, this is going to be the plan. So start with your original passive secure protocol. Our transformation will work for ones that have a particular natural structure. The definition, as always, the definition of natural became a little bit gross. I don't know how natural it is, but the good news is that it's at least satisfied by essentially any protocol that's out there. Of course, you can design a horrible protocol that does not satisfy this, but the natural ones do. Okay, so take your semi-honest protocol, and such a natural protocol has the structure that up until the very last message, actually you're not learning anything. You're just basically sending out secret shares of things. It's basically garbage. And then at the very last round, you will send the final message, which sort of reveals what all this garbage truly meant. I have like 2 very detailed slides of an example of a proof that I've skipped over here, but I can show them to you after if you're interested. Okay, so trust me on this. So our plan is going to be to run the semi-honest protocol up until this very last round. Okay, and stick in an extra stage here. And by the way, this framework is not new to us. But how this will be implemented will be different. Again, the goal will be to somehow stop, freeze frame everything right here. And before you send this message, which could reveal information, and by the way, so the guarantee is that if people really acted semi-honestly here, then whatever is going to be sent is safe. But if people were cheating here, sending this last message might reveal my input. Okay, so I don't want to send this unless I'm convinced that all of you were actually acting semi-honestly up in the first part. And this is what we're going to stick in here. Okay? So if in this phase, somebody's not convinced, then they'll just abort. Okay, so we're not getting like a guaranteed output delivery, but some kind of security with the board. And you can actually build on top of this in certain cases to also ensure conclusion. Okay, so just kind of very, very briefly, let me describe one way that you can kind of execute this blue box. And it turns out there's different sorts of blueprint frameworks of how to stick this in. So I'd be happy to talk about that another time. Okay, so what's going to happen? Our execution of this type 1 is that at this phase right here, each and every party who's running in the protocol is going to separately act as prover to everybody else. And the other parties in the protocol are acting like the multiple verifiers. Okay, what am I proving? What is even the statement of the language here? My input, my X, is going to be just a concatenation squashing together each and every message that I ever sent out or received to anybody. Okay, note that I know this completely because I sent or received it. And each of you have exactly some piece of that, which is my communication to and from you. Now, what is the thing I want to prove? I need to assert to you collectively that the combination of all of these messages were computed as they were supposed to, as dictated by the protocol. And as it turns out, you know, in these detailed slides, for these natural protocols, essentially everything that's out there, the computations I'm supposed to do in each and every step is a degree 2 function. Okay, so I receive messages from you collectively, various pairs of these things I kind of multiply, maybe I add something, and I send that out to somebody else. Okay, so this is exactly the setting where we have good solutions, where we have these zero knowledge proofs on distributed data, where the proof size, this extra communication, the secret shares of pi that had to get sent were small. They were sublinear in the X that we began with. Okay, so what do we end up doing? Again, so you run the first part of the protocol. Before you send the last message, each and every one of us proves to everybody else that these messages from the first part were computed correctly. And if it truly is the case, if everybody is accepting, that means that this gray part here was done correctly. And that gives you that it's safe to reveal your final message. Okay, and what is the overhead in the communication? Well, it's really just this extra communication of this protocol for each party acting as a prover. And by the way, you can also do them all in parallel. You don't have to do one by one. And collectively, this extra communication really amounts just to the proof size, which we said is sublinear in the original communication of the first part of the protocol, plus whatever the verifiers are communicating, which also turns out to be quite small. And kind of bottom line here, so this extra communication is sublinear in the circuit size. So this is what I promised you at the beginning of the talk. I'm not going to say anything about this. Let me just sort of tease you with everything that I've described works in the setting where you have an honest majority. And this comes into play because I do need some sort of robustness of the messages that are here. Remember, we said that there was something there. Turns out this does hold for honest majority protocols. The question, if it's the case that everybody except for one party is malicious, then things become more tricky, but also more interesting. And it turns out that you can still apply these techniques. So you can ask me about that. Okay, so to conclude, what did we have on our journey together today? So kind of the takeaways that I want you to remember, first of all, this notion, the zero knowledge on distributed data, I think it's quite interesting, and I think it has a lot of potential applications. A little bit about construction, so this notion of fully linear Pcp or an interactive version we didn't really say much about. And the fact that for simple languages, that you can do this with very small sublinear proof size. Okay, and some of the positives here, so this is this step that we're sticking in this blue box, we're sticking into the protocol, does not add any computational assumptions. So whatever the original protocol needed, that's exactly what the final protocol needs. And also something very cool, it works automatically for any field, and in fact, rings of form Z mod n. That means for free, you can do this in the setting for Boolean circuits. You can do it for big fields, you can do it for small fields, you can do it for computations over the ring Zn. And you don't need to come up with specific targeted protocols for each of these cases, which is what you used to have to do in kind of works beforehand. So in particular, for example, the Boolean case, there's a lot more complication because you get small, like bad soundness and so forth. Again, as I mentioned, this gives you these applications, just a linear communication overhead of going from passive to active security. I think I'm sort of overstayed my welcome here for this talk, but just to mention a couple open questions. There's a lot of really interesting directions, trying to build better underlying tools, trying to look at different passive to active compilers. For example, we still need certain type of structure on the original protocol in order for this to go through. And there's a lot of other types of protocol structures that exist out there. It'd be really interesting to try to see if you can extend these. For example, even just if instead of addition and multiplication gates, you had more rich sorts of basis of gates for your circuit. Okay, and with that, I will conclude.
In the interest of time, let's have one question.
I was wondering if you can say something more about linear PCBs, whether we want to like computation and the number of queries you should need for languages, whether you can prove something is in a language with fewer queries than normal PCBs.
That question I think already applies even in from here to here.
Yes, exactly.
Yes. So there are. Actually, I don't have a good quick answer to give you, but there are definitely settings where this does give you more power. I have to check a little bit to see.
Okay.
All right.
So I understand some of you have to check out the video. The straight session slightly later, 10:45. So that's 15 minutes.